All right, so let's get started. Today we will, as you hear, I'm still struggling a little bit with a cold, so I hope my voice is going to carry us through this lecture. Today we're going to continue to talk about the physical layer, and in particular we're going to start to talk about noise and how to characterize noise and how to calculate performance in terms of bit error probabilities and symbol error probabilities when we are transmitting data over a channel which is noisy. So remember last time we talked a lot about pulse amplitude modulation and different pulse shapes and how these pulse shapes can be chosen in order to avoid intersymbol interference. Okay, so that to avoid intersymbol interference is a pretty common design goal. So this is something that we would like to do. And if we do that, it also means that we're limited by the bandwidth in how much symbol rate we can use over a channel. So the symbol rate, which we want to have high, is upper limited by the bandwidth, according to some formulas you saw them last time. But essentially, we cannot, for sure, cannot communicate with more than twice, where the symbol rate can at most be twice the symbol. I'll try again. The symbol rate can be at most twice the bandwidth of the channel. Okay. And one way to implement ISI-free transmission over band-limited channels, we need to select then the pulse shapes very carefully. And what we want to do is to make sure that the convolution between the receiver pulse and the filter at the receiver should fulfill a criterion that looks something like this. So these are the raised cosine pulses. The total bandwidth of these raised cosine pulses is W, and it's characterized by this parameter alpha. So alpha is a design choice. We can choose alpha what we want as long as it's greater or equal to 0 and less than 1 also. So it's a number between 0 and 1, and then we get a family of different pulses. And what it does, it affects then the bandwidth of the transmitted pulse. So if the bandwidth is limited, okay, then the symbol rate is reduced by increasing alpha. So the bandwidth W is 1 plus alpha over 2t. And 1 over 2t, we can think of that as the minimum bandwidth we need in order to support ISI-free transmission at the symbol rate, which is 1 over t. Okay, and the rest, this alpha here over 2t, is the extra bandwidth that we allocate to our problem. So this is what we can say, we sacrifice some bandwidth in order to make life easy for us. So by selecting alpha a little bit greater than 0, we need some extra bandwidth, but on the other hand, we show that the pulse system has a nicer properties in the sense that it decays faster in time. Okay, so instead of having a very long duration, effective duration, then we can actually truncate it a little bit more aggressively. Okay, now, so since we are saying that we have now specified the convolution between the transmitted pulse and the receiver filter, so how should we select the transmitted pulse and the receiver filter in order to do this? Many ways to do that. The standard way to do that is to make sure that the pulse Fourier transform fulfills what's called the root raised cosine spectrum. So that's basically take the spectrum for a root raised cosine and take the square root of that. We get the root raised cosine. And this is the time domain expression for that. And from all these formulas, pretty clear that if we have the receiver filter, the transmitted pulse and receiver filter being the same, then the convolution of those, the Fourier transform that, is just the product of the spectra. And since each individual spectra is the square root of a raised cosine, then the product is, of course, the raised cosine. And then we have ISI-free transmission. So this is the typical way to do things. Now, spectral efficiency, what is that? Okay, so The objective with selecting pulse shapes are twofold. We want to make efficient use of the bandwidth we have to our disposal, and we want to avoid ISI. If we select a pulse according to this, with this we select an alpha, then this is the bandwidth needed for this. And the question is, what is then the spectral efficiency? How efficient are we using the spectrum? And the way to measure that is through this variable nu, which is the data rate in bits per second divided by the bandwidth. Okay, so this holds in general. This is just a definition. So whatever system we have, we can calculate the spectral efficiency according to this. Now, if we use M-ary PAM with a root raised cosine pulse shape with this factor alpha, then our spectral efficiency is 2 times the log 2 of m, so twice the number of bits we transmit per symbol, divided by 1 plus alpha. And remember, alpha is a number between 0 and 1, so the smallest it can be is 0, and then we get the spectral efficiency, which is just twice the number of bits per symbol. Okay, so this is the highest we can hope for. If we increase alpha a little bit, we reduce the spectral efficiency accordingly. So reducing the spectral efficiency is not good, so why do? We do it because then the implementation becomes easier. Okay, so it might still be a good thing to do. Okay, then we started to talk a little bit about so here we have pulse amplitude modulation of some data, and we have a receiver filter here, and then we have talked about sampling this, and we would like to have ISI-free transmission here. And then we started to talk about the rest of the receiver here, and we will finalize that discussion today. But this is a typical block diagram where we have a transmitter here and the receiver here. And now, recall now that we have made a simplification here to say that the pulse shape that we transmit here is H, and the receiver impulse response is matched to H. So an impulse response which is matched to this is the pulse conjugated and then time reversed. All right, and then we will talk a little bit about this slicer in a moment. And this block diagram turns out to be a minimum distance receiver for PAM if H is chosen such that it's a root raised cosine pulse, so which means that H convolved with the receiver impulse response here is a scaled Nyquist pulse. And scale, what do we mean by that? Is that if we take T-spaced, capital T-spaced samples of the overall pulse, the transmitted pulse convolved with the impulse response of the receiver filter, then we get something which is non-zero when k is equal to 0, and 0 for all other samples. Okay, so this is the Nyquist criterion. And what we get at time 0 is simply the energy of the pulse H. Okay, and that is always positive, right? Okay, so let's continue now a little bit to talk about, so one thing we did not have time to talk about is what is this slicer thing here. And essentially the slicer is just a minimum distance receiver working now on discrete input. Okay. So what we would like to achieve in general is a minimum distance receiver based on the received signal R, and we should put out the corresponding symbol here. And now we've done some processing here in order to convert this to a discrete variable here, which is input to the last box here. So, slicer. So we have some input to this box. Which we call Z, and then the output is A hat. And as a side information to this box, we have the set of all possible amplitudes, curly A. So the output is the element in A in curly A that is closest to the input okay. So what do we mean by closest? Well, first of all, we take the input, which is Z, and then we subtract off different all the different elements in A, curly A here, so all the possible amplitudes here, and then we minimize the distance between Z and A. So since Z is just a number, it's the magnitude, the absolute value difference between Z and A. Okay, and we form A hat as the arg min, where we this variable A, we vary that to be any member in the set curly A. Okay, remember that Z is the input, and then we check for all possible A's, and then we select the one which is the best, which is the one that minimizes the distance here, and then we call that A hat. Okay. So a small example to clarify this. So suppose that curly A is -3, -1, 1, and 3. So 4 different amplitudes. Then what we need to do is that for any input Z, we need to specify what the output is. Okay. So one way to do that is through a graph, where on this axis we have Z, and then for each value on the Z axis we need to specify what the output is. Okay. So, and the output is A hat. And basically I just need to draw the graph for this. Okay, and one way to do that is to first of all plot the values of the elements in A, the possible transmitted amplitudes, and we have here -1 and -3, 1 and 3. Let's draw small dots here. Okay, so these are the possible amplitudes in A, curly A. And then but Z can take on any value, right? So the question is what we should output here. So let's start from the left. So if we're to the left here, we will always be closer to -3 until we're right in between -3 and -1, right? So between here at -2, any value of Z which is left to this one will be, what would be the output then? So the output could be -3, -1, 1, or 3, and we should pick the closest one. So if we're to the left of this border here, what should we pick then? -3, exactly. So, so anywhere to the left of this point here, the output is -3. Once we hit the border here, that is right in between these 2 points, then we are at the same distance from -3 to -1, and here we can actually pick any value we like. But when we go over the border into that region here, we will switch over and then output -1. Okay, here. Okay, and then we will continue to have -1 here until we hit the next border. And the next border is right in between -1 and 1, that is at 0. So we go like this, and then it will be symmetrical on the other side. At this point, we will select 1 until we hit the border between 1 and 3, which is at 2. And then we will hit 3 when we go to the right for that. Okay. So this curve here defines then the relationship between the input, z, and the output. And the output is discrete, right? It can only take on 4 different values in this case. -1, -3, -1, 1, or 3. Okay, so it's going to be a staircase function of these sort. Okay, any questions on that? Okay. So typically we don't draw or illustrate these type of decision rules in this way. Rather what we do is that we look at the z-axis and then identify which intervals corresponds to what decision. Right? And we call these decision regions. So for instance, if we want to find the decision region for -3, we find all the z's that corresponds to that decision. Okay, and all those z's are the z's which are to the left of this border here. So this part of the axis here is called the decision region. For a hat equals -3, right? So we will have as many decision regions as we have signal alternatives, in this case 4. So this will be the decision regions. All z's less than -2 will be mapped to the decision a hat is equal to -3. And then if we go to the next decision region here, and then I will just draw it something like this. This is the corresponding decision region for decision -1, right? And then I'll continue with yellow here, and then we have the decision region here, which corresponds to a hat equals 1. And then we have the 4th region, which starts here and then continues forever. Okay. So basically what we did is that we split the z-axis into 4 intervals, 1 for each possible output. That is, 1 for each possible amplitude. Okay, clear? Questions? No. Okay. So,
Sorry.
Yes.
What if you are right on the border?
Okay. So what happens when we write on the border here? And then what that means is that if it's like this, we're equally close to -3 to -1. Okay. And then we can actually select either of them, either randomly or just take the smallest one or the largest one of these two. It really doesn't matter. But we can think of it to just make it easy for us that when we end up here, we flip a coin and then we pick one of the neighbors with equal probability. Okay. And the same is for all the borders here. So specifically, so we haven't really specified the point when there is a step in this decision. But that's a good point. Okay, now plotting z here and plotting these constellation points here. These are called constellation points. That's a way of visualizing how the modulation schemes work, right? So these constellation points, we will see constellation diagrams. We will see them a little bit more in the future here. And typically, from a constellation like this, we can deduce, as we will see, we can deduce a lot of properties from that modulation scheme. Okay. So let's now continue into looking at this receiver. And previously what we have done is that we have ignored the noise, right? We put that to 0 and we try to design H here to make sure that there is no intersymbol interference here. Okay? Now suppose we have done that, and now let's see what happens when we have noise here. Well, then there will be a noise contribution in this variable here. And that noise contribution will make yk, or rather zk, not being equal to ak anymore. What we will have, since everything is linear here, zk will be equal to ak plus a noise contribution, where the noise contribution is whatever noise remains at this point in the processing diagram here. Okay, and what we want to do then is to calculate what is the okay, so how should we treat noise? And this is actually an important step in the modeling of things. And this is typical what we do. Noise is something that is inherently difficult to predict. Right? It's something that we're unable to predict. If we can predict it, it's not noise. Then we can subtract it off, right? So noise is something which is unpredictable. And when we have something which is unpredictable, the standard way to model that is to model that as a random quantity, a random variable or a random process. And I would say that this is a super important modeling step, not only here in physical layer, but in life in general, I would say. Engineering for sure, but also in life. I mean, things happen which are not predictable, right? So one way to think of life is that it's random, which is true to some extent. Now, one can also ask oneself if nature by itself is random or deterministic. And that's actually a very interesting question. But it seems to me that it seems to be random, in the sense if we believe in quantum mechanics, for instance, then there seems to be in nature there is inherent randomness. Okay, we will not go into the philosophical details here, but basically say that okay, we have some disturbance on the channel, we have no idea what it is, we have very limited ability or no ability to predict what it's going to be, so we just have to live with it. Okay. And the question is, what type of processing do we need to do in order to minimize the negative impact noise has on our ability to communicate? Okay. And by the way, one way to, we will not go into deep proofs of this, but actually this is a very good choice of receiver filter. It's the best choice, actually. Okay. Of course, under some modeling assumptions, right, that will be clearer later on. But we need to model life as random, or at least our block diagram here is random. Okay, so then now a short overview of some basic concept in probability. And then I will talk a little bit on how to extend these concepts into the concept random variables, how to extend that into a sequence of random variables, which we call a random process. For some of you, this is old stuff, and for some of you, it might be new stuff. For some of you, it's old stuff that you forgot, right? There are many possibilities here. But on the home page, there is a link to an online course in probability, which I think is fairly good, right? So if you feel like you need to brush off your knowledge in this, I encourage you to go to this course. And again, I would say that there are few things which are more important to learn in a college engineering program than to be able to handle random quantities. Okay? Regardless if you do communication, signal processing, if you measure things, if you design things and things like that. Everything we do are more or less relying on how to deal with randomness. Okay? When we want to design something, we want to make that robust, right? Robust to tolerance and things like that. And how do we do that? Well, we do some random modeling of this. Okay, so now I've done this big speech about this. So this theory, it's not only very useful, it's also a lot of fun. It's not a lot of fun the first time, but it will be after a while, because then you have an advantage over the rest of the world by understanding these things. Okie doke. Probability mass function for a random variable x. Okay, it's when x is a discrete random variable, which means that the outcomes of x are picked from a finite set of numbers. So for instance, that set could be this set. If we pick something randomly from this set, we get a random, discrete random variable. So then we can specify something called the probability mass function. So F for probability, sort of, subscript X for the random quantity, random variable, and then it's a function of this variable U. I mean, it could be V or T or whatever it could be. Sometimes very often it's small x. Let's go with U here. So what is that? It's the probability that X takes on U. Okay? And this specifies our preconception of the variable X. Okay? So if we know the probability mass function, we don't know what X is, we just know how probable X will take on different values. And that's all we can know about a random variable before we actually observe it. Once we observe the outcome, it's no randomness left, right? But before we observe something, this is what we know about it. Okay. For continuous random variables, one cannot do this. One cannot define the probability mass function. One has to do it in a slightly roundabout way. So for continuous random variables, these are X or random variables that can take on a continuum of values, maybe all real numbers, for instance, say all the numbers between 0 and 1, all real values between 0 and 1. So that's a continuous random variable. For that one can define a probability that X takes on a value which is less than something. Okay? And this is called the cumulative distribution function. Okay. Once we have this, we get something which depends on U. So it's U here is a continuous variable, like the real numbers, for instance. And it could be like this function here is differentiable. If it is differentiable, we can compute its derivative, and then we call that the probability density function. Okay. All right, so once we have the CDF and the PDF here, we can calculate different types of probabilities which are useful for us. For instance, the probability that X takes on a number which is greater or equal to A and less or equal to B. How can we do that? Well, we can split this event, that X is less than B and greater than A, into two events. The probability that X is less than B, okay, and then we subtract off the probability that X is less than A. Okay, and then we get the probability for an interval. And once we have it in that form, we're very happy, because then it's by definition equal to the CDF. And then we could just put in the CDF here and here, and then we plug in B and A, and then we get the probability we're looking for. If we don't have the CDF, but just the PDF, we can get the same thing by integrating the PDF between A and B. Okay. So does this seem familiar? Yeah? Okay. Good. If it's not, then have a look at the review material. Okay. Something that we were concerned about is expectations, and there are different types of expectations. And the simplest one is that what is the expected value of A? Sort of like the average. And so the expected value, or mean or average, of a random variable, and now we look at continuous random variable. It's E for expectation and then X. So E here has nothing to do with energy or something, anything like this. You see it's like it's with a different font here. So this is important. So this is the expectation of X, and that's by definition this integral here. And if we, instead of having X here, has a function of X, where G here is a deterministic function. If X is random, then G of X is random. So this is a random variable. And the expectation of that random variable, we get that by simply, instead of having U as we have up here, we have G of U here. And then it's the same integral. So one thing which is important, except for the average is an important quantity, the second moment is also important, and that's the expected value of X squared. So that's for a particular G function. So we just put in G here being the square function, and then we see we get U squared here in the integral. Okay, and then we can compute this integral. I mean, it doesn't always converge and things like that, but we won't be so mathematically strict here. So we will just think that these integrals exist. Okay, and then the variance is the expected value of this thing. And what we see here inside the parenthesis here is the random variable x, and then we have subtracted off its average, its mean. Okay, so x minus its mean, it's the deviation around the mean. We can think of that. And then we square it, so we get always a positive number. And then we take the average of this. Okay, so e of x here is just a number, 15 or 22 or negative 87 or something like that. And then x here is something which is random. So here we have, again, a specific function g of x. And then we use this definition to figure out what that should be here. Okay, so it's u minus the expected value of x and the whole thing squared, and then we integrate this. So this is the variance. So the variance tells us something about how much the random variables outcomes is distributed around the mean. A large variance means a lot of difference. A small variance means small difference. Okay? Right. Statistical independence. Yeah, before I go. For discrete random variables, it's the same formulas except for integrals is summations. Statistical independence is when we have several random variables that are in play at the same time. So for instance, if we have two random variables x and y, we say that these are statistically independent if the following criterion is fulfilled. First of all, here we define a function which is the CDF now over the joint variables. So x and y are the two random quantities in our world at this moment. And then we can calculate the probability of the joint event that x is less than u and y is less than v. Okay. So we have two random things. And then when we observe them simultaneously, what is the probability that x is less than u and, this comma means and, y is less than v. If this happens to factorize into the product of the individual probabilities, then we say that these two random variables are independent of each other, statistically independent. Okay, and if they are, we can then factor the joint CDF into the product of the individual CDFs. And also, if we differentiate the right-hand side here, we can see that the PDF, which is the derivative of this with respect to u and v, factors as the product of the PDFs, these individual PDFs, sometimes called the marginal PDFs. And if we want to calculate the expected value of x times y, then by definition it's this double integral, but luckily for us, it factorizes as the product of two expected values. So this thing about independence is basically that if we have two things which are unpredictable, if we really don't see how they could possibly be connected to each other, then we can assume that they are statistically independent. So this independence is often based on an assumption. So for instance, the temperature outside this room, outside, is probably a random variable. We don't know what it is until we have measured it, right? We know it's going to be rather cold, right? But that's it. There's going to be some distribution around it. We know it's not negative 20, and we know it's not positive 20, but we're not quite sure if it's +2 or -1 today, perhaps. We don't know, right? So it's unsure to us. But if we measure it, we can figure out what it is. Now the temperature here is probably independent of what the temperature is in Miami right now, right? They're not really connected. Of course, they're connected through the global weather and all these things, but it's unlikely that that connection is very strong. So we can think of these as statistically independent random variables. However, the temperature in this courtyard and the temperature outside this courtyard are probably a little bit different because of the physical properties of the courtyard and so forth, but they are highly dependent, right? It's not going to be very different from inside to the outside, regardless what the value is inside the courtyard. Okay. So that's in the nature of statistical independence. So it's like a modeling assumption we do based on our understanding of the problem at hand. Okay, questions? No? Okay, so now let's go into some details here and see how this random modeling helps us in building understanding for physical layer. And again, we want to do that from this type of perspective here. And we have two things here actually that are random. Noise, which I already argued for why it has to be random, because if the noise is not random, then it's predictable. We can figure out what it is, and then at the receiver we could just subtract it off, right? We don't have to deal with it. Okay, so there is one. So that's, I think, fairly clear that noise has to be modeled as random. But there is also one other thing here which we model as random, which is less obvious at the first sight, but it sure makes sense. What could that be? Well, think of it like this. I'll give you a hint. Suppose we are the receiver. Okay, so we would like to then figure out what the transmitter sent. Do we know what the transmitter sent? No, of course not, because that's the whole problem, right? We need to figure out what it sent. So for us, the transmitted data is random. It's unpredictable. We don't know it with certainty what it is. If we knew what it was with certainty, there is no need to communicate because we already had the information. So from the receiver's perspective, if I'm standing here and looking at this way, the data which is transmitted is random for me. Right? I don't know what it is. I can have an idea what it could possibly be, right? Maybe with some probabilities, but for sure I don't know exactly what it is. Okay? So we will model the transmitted data as random. Okay? And implicitly what we think about is from the perspective of the receiver. From the perspective of the transmitter, it's not such a big thing. It just got it, right? It's not random at all. And then it just sends the data. But for the receiver, it's quite unknown. We don't know what it is. Okay. So this is a discrete random variable, right? It can take on values which are in the constellation here, in the curly A, okay, some randomness. So what do we need in order to characterize that? Well, we need to figure out what is the probability that the data takes on different values here. And we actually go one more step, and that is to figure out that, and from our understanding, that the symbols here, the amplitudes here, depends on the transmitted bits. Okay? So let's start with the bits and see how the probability for the bits then imply what the probability for the symbols are. That is that the transmitted data takes on any of these numbers here with what probability. Okay? So I'm going to close down here a little bit and then use the blackboard now for most of the remaining lecture here. So the transmitted bits. So we model, okay, and with the word model is that implies that now we're making a statement about reality that might not be perfectly aligned with reality, but is good enough for our purposes. Okay, so we use model all the time, so we should not be worried about this. So we model the ith transmitted bit b sub I. I is the time index, 1, 2, 3, 4, etc., as a discrete random variable. And it's not only discrete, it's actually binary. So it only can take on two values, 0 and 1. So this is probably the simplest random variable we can think of. Flipping a coin is an example of this, right? So how to characterize this? Then we state what its probability mass function is. Okay, and so F for probability mass function, or PDF, and then subscript for the random quantity, and that is BI. Okay, so that's what's random. And we know that BI can take on two values, 0 or 1. And then we have a discrete variable U that can take on 0 and 1. And what is the probability that BI is equal to U? That's the PMF. Okay, so by definition, this is what it is. And suppose the probability that the bit is equal to 1 is PI. Okay. So this probability, PI, has to be some number between 0 and 1, right? Because it's a probability. So what is the probability that the bit is equal to 0? Given PI is not necessarily 1/2.
1 minus PI.
Exactly. So it's 1 minus PI. So actually, it's enough. If we want to characterize the PMF, we don't have to write it up, the whole thing. We could just take one of these numbers, and then the other one is implied. Okay. So the binary random variable is very, very simple. It's specified with one parameter, namely its probability to take on, say, the value 1 or 0, whatever we prefer. Okay. Now, so this was quite general in the sense that we say that the probability can be a function of time, right? For different time indexes, we might have different probabilities. This is way too complicated for us to deal with in this case. So we'll just say that we think that all these probabilities are the same. Okay, so there is no difference between the first and the second bit, or the third bit and fourth bit. They all have the same statistical properties, same probabilities. So we will often, or almost always, assume that BI for I equals, say, 0, 1, etc. is a sequence of equally likely and independent random variables. I will use R dot V dot for random variable because it's going to write a lot of random variables otherwise. Okay, so what does that mean? Well, first of all, it implies that the probability that the ith bit, remember I again is the time index, is equal to U. This does not depend on I. Okay, it's the same for all i's. So that means that it's and then all of these happens to be equally likely ones and zeros. So this is equal to 1/2 for all I and U. Okay, question?
How big of a simplification is that compared to how it is in real life?
It is not so bad as one might think, but obviously it's not true, right? So if we think of, for instance, if we want to transmit an IP packet, we know that the IP packet has a certain structure, and in the address fields, for instance, maybe zeros are more common than ones and things like that. So then the probability for those bits would not be 1/2. But as we go into the payload, then it's much more unclear what that could be, because that's user data, and that we simply don't have a good hold on. So it's not this is a simplification, but it's not so bad as one might think. And it sure makes life easier for us, as we will see later on. So this is a typical assumption being made. Okay, so then let's continue here then. So then the probability for a sequence of bits taking on a certain bit pattern. So say that we take k bits here. We start with B0. What is the probability that is equal to U0? And, comma means and, B1 takes on the value U1. And then we continue until we get to B, say, capital K minus 1 equal to U capital K minus 1. So here we have capital K bits, right? And then we have specified some bit pattern, and we would like to, and we would like to calculate the probability that our bits B0, B1, etc. takes on one specific pattern, which is determined by U0, U1 up to U capital K minus 1. So what is this? Well, due to independence, we can factor this. So we can write this as B0. This joint probability is the product of the individual probabilities. So the first factor is B0 equals U0 times the probability that B1 is equal to U1. And then we continue until the last factor, which is the probability that the last bit that we consider, which is B capital K minus 1, is equal to U capital K minus 1, like that. Okay, so this is due to independence. Independence. Okay. And then we use the fact that all bits have the same probability to be 0 and 1. It doesn't depend on U, and it doesn't depend on I. So all of these factors are equal to what? So this one is equal to 1/2, right? 1/2, 1/2, 1/2. The whole thing, 1/2 to the power of K. Okay. And this is equal to 1 over the power of 2 to the 1 over 2 to the power of K. And I mean, we knew this already more or less, right? If we have K bits, how many patterns are there? The 2 to the power of K. If they're equally probable, what would be the probability for one particular pattern? Well, it has to be 1 over 2 to the power of K. Okay. Okay. But anyway, so we did it in some other way. Now, so what does this have for implication? Well, think of it that we have binary PAM here, and then we have here B0, B1 up to BK minus 1. This corresponds to one block into the PAM modulator. Into the mapper, which then outputs a symbol that we want to transmit. Okay, and so in this case it would be the first symbol, A0, right? So it takes the first capital K minus 1, the first capital K bits and then maps into this. Okay, and we know that the symbol A0 is a member of curly A, which is the set of all possible amplitudes. And we had A1, capital A2 up to, and the last one is A capital M, like this. Okay. We said this before, the number of output amplitudes has to be equal to the number of possible inputs. So we have here 2 to the power of k possible inputs, which means that m here, of course, has to be equal to 2 to the power of k. So then if I ask you this, what is the probability that A is equal to one of these here? Let's call it AN. One over m, correct. And how did you reason there?
1/4 through all the
Yeah, exactly. Well, one can think of it like this. The randomness here in these symbols depends on the randomness of the input here, right? So each possible amplitude here corresponds to one particular input pattern here, right? All the input patterns were equally likely. Therefore, all output amplitudes are equally likely. There are capital M of those, so this must be 1 over m. Or, if we like, 1 over 2 to the power of k. Right? So this is typical, right? We have something which is inherently random, okay, and then we do something with it. And if this processing here is deterministic, then the output is still a random thing, but the randomness in this output depends on the randomness of the input and the type of mapping which is done inside the box here. Right? In this case, it was super simple, right? Because then if there's equally likely inputs here, then the output has to be equally likely also. There cannot be in any other way. In some other aspect, it would be more complicated, right? If there are certain patterns here which are more likely than others, then that would imply a distribution which is not equal, uniform over all these amplitudes. Okay. So just an example to reinforce this. So say we have B0 and B1, so capital K is equal to 2, M is equal to 4. So we need 4 amplitudes, A1, A2, A3, and A4. Corresponds to the input patterns, and just arbitrarily assign these to A1 to A0. The pattern 0, 0 to A1, 0, 1 to 2, 1, 0 to 3, and 1, 1 to this. Okay. Then the probability that small a is equal to A1. What is the probability that A0 is equal to A1? Well, it's the probability that B0 and B1 is equal to 0, 0, right? So this is the same thing to say that B0 is equal to 0 and B1 is equal to 0, like this. And what was the probability of these things? Well, it's the probability of B0 equal to 0 and probability of B1 equal to 0. It's 1/2 times 1/2 or 1/4. Okay. And this is what we expected also. We have 4 possible outputs. They're equally likely, so the probability for one particular output is 1/4. Okay, good. Questions? No? Okay, so now let's continue. Now we know how the randomness in the bits implies a randomness in the amplitudes. And now let's see what that means in terms of the transmitted signal. So the transmitted pulse is now also random, right? So okay, so what is it? Well, it's A0, so the amplitude that we transmitted, times the corresponding pulse shape. And since it's the first symbol is just the pulse shape itself. So this is the transmitted pulse. What is the energy of this? Well, by definition, we know the energy is simply the signal magnitude squared integrated for all times. So it's going to be A0h magnitude squared and then integrated for all times. So this is the definition of energy, right? Okay. And we can then break out A0 magnitude squared because it has nothing to do with the integral. And then we have the integral from minus infinity to infinity of magnitude squared of h dt. Okay, and this integral, we've seen that a couple of times, and this is simply the energy for the pulse shape h, so E subscript h. So, what can we say about this thing? Well, first of all, it's the amplitude, the transmitted amplitude. And the transmitted amplitude is a random variable, right? Because it depends on the data that we transmitted that we model as random. Okay. So this is random. Okay. Which means that the transmitted energy for a particular pulse is a random quantity. It's not fixed. It depends on what the outcome of the bits were, right? Because for some of the bits, this amplitude will be large. For some of the bits, it will be small. So in general, the energy per pulse for a particular pulse is not determined. It could vary. It could take on different values. But we can calculate its average or expected energy. Okay? So the average energy okay, and now here it becomes a little bit complicated what E and E means, okay? But the average energy, we denote that by E subscript S, okay? So it's the average energy per symbol. Okay. So what is that? Well, it's the expected value of the energy per pulse, right? The energy per pulse is a random quantity, but on the average is something. So it's the expected value of the average energy per pulse, which is the expected value of A0 magnitude squared times EH. Okay. So here this is the expectation operator. Expectation is something which is linear, which means in the, that one can